We're going to be taking a look at the fundamental theorem of linear algebra. And this is going to give us a more concrete way of looking at what happens when we add lots of equations to a linear system. So fundamental theorem of LA. Okay, there's a lot of writing in this video, so get ready. I'm going to be putting it all on the screen here so you have it all. It's a lot of, theoretical stuff and everything. So you want to make sure that we're really taking in all this information. So we're going to start off with a bunch of linear equations. So start off with a bunch of linear equations. And the dimension doesn't matter in Rn. Well, it does matter, but it could be any dimension, right? So we're not going to make any specifications for that. We are going to really make this as general as possible. So we can have a bunch of equations, right? So, we have them written out over here. So we'd have equation 1, equation 2, equation 3, and so on, right? And so on and so on. So we're going to have n variables per equation. And you can have as many equations as you want, but you need to remember, right? Like I said in the last video, every time you add a new equation, that's one more person that you need to satisfy their needs. And we know that people don't agree on anything. So if you were to have a ton of equations, you're just going to make it impossible to satisfy each one, right? We want to find variables x, y, z, and so on that will work to make every equation true. But if you keep adding equations, at some point, if they're not going to be multiples of each other, then you're going to just have an empty set of solutions because no solution will satisfy all those conditions. You have to keep that in mind. You can add as many as you want, but if they're not multiples of each other, you're going to start having a lot of problems. Let's get a bit of writing down here, a bit more writing, because there's going to be so much in this freaking video. So there we go. Okay, so number 1 over here, let's go ahead and get some stuff out. Each equation has a solution as a hyperplane. And we've learned about these hyperplanes, right? We've seen them earlier on in this series. And this hyperplane is going to be in a dimension. So hyperplane in, let's say in Rn, will be in dimension n minus 1, right? That's what you're doing with the hyperplanes. You are essentially freezing one of the variables and making it work in a dimension that is 1 lower. And it's a concept that fools a lot of people. I'm going to also have a lot more work on hyperplanes up later on in this channel, some things that we can use to study them a little bit more. But they're going to be crucial to solving, things like this, right? Once we actually get to start solving some practice problems, it's going to be crucial to be able to, understand why we need the hyperplanes. So we'll go ahead, number 2 here. The set of solutions is the intersection of each equation's respective hyperplane. And we saw this in the last video, right? I said that when we had 3 equations of 3 variables each, then in order to find the intersection, we are going to need to find the intersection of the hyperplanes. And we're doing this sort of kind of like with a set theory, right? So we have hyperplane 1, all the values that the hyperplane 1 holds. Then we have this, the intersection with hyperplane 2, so all the values that it holds, with the intersection of hyperplane 3, and all the way with all your hyperplanes. So all the values that these hyperplanes hold, you need to find the area where all those hyperplanes are going to be true for whatever values you are going to be taking, which is difficult, right? I guess leave hyperplane n there. I could probably put k there, but I'll leave n there for that subscript. So, there we go. So let's go. So therefore, the more items you're adding here, the more equations you're adding here, it's possible for your solution. I'm going to put k here instead of n. For your solution to be empty. Especially if your term k over here is very high. Very large, and we'll add more, your equations are not multiples of each other. So we saw that if the equations are multiples of each other, so I'm talking about something along the lines of x plus y plus z is equal to 1, and 2x plus 2y plus 2z is equal to 2. So these are going to be the same. These are the same essentially, because if they're just going to be multiples of each other, so all the variables and your final result are all multiplied by the same value, then it's going to be the same answer, right? We're going to get that situation where we're going to have the planes on top of each other. Like literally, they're both parallel and on top of each other. So they are always intersecting, and therefore essentially the same thing. So always intersecting. So we're saying here that it's possible for our solution to be an empty set. Now, there's also some other possibilities where we're actually going to get some answers. So the possible answers, possible solution, we have empty. And you're going to see why we're doing this. I'll probably cut this up into the next video. You're going to see why we're doing this. When you have non-linear systems, you'll be able to weed it out and say, nah, not going to allow this. Say you have x squared as one of your things, right? If you suddenly had x squared over here, you don't have that linear system anymore. You're going to have something that's more quadratic, polynomial. So you don't want to have anything related to that. So it could be empty. It could be a point. It could be a line. It could be a plane. It could be space. So this is the one for 3D. And then you can have all the other options, right? So everything, so on and so on as you go through your dimensions. If you go to 4 dimensions, fifth dimension, you have all those other options that are going to be available. We won't bother to focus on talking about those. And you just have them, going on forever. So one more thing to close off with here, right? One more thing to close off with. Maybe we'll just make this like a marathon video and we'll just cover everything. So let's have an instance here with our hyperplanes. This is hyperplane 1. Down here, we'll have hyperplane 2. And then we have this one over here is hyperplane 3. So we can see some intersections here. We see that hyperplane 1 and hyperplane 2 will intersect, let's say, right over here. And over here, you'll have 1. So by set theory over here, this line is going to contain H1 H1 intersection H3, and this line over here will contain H2 union. I said it again. Fuck. Intersection H3. When I just make a stupid mistake, it just stays in my mind and I can't zone it out, and it just stays there. So what is the solution over here, right? We see we have two parallel lines over here, and it's not going to work. That means there's clearly not going to be some answers that we can put for our x, y, z variables that are going to allow us to have all the equations satisfied. So this is a situation where we're going to have no possible solution, right? So this is a place where we'll have no solution. No solution. It's one example where it won't work. I'm going to end off. I'm trying to see how far do we want to go here? Are we just making this like an absolute marathon? Let's just do that. Let's just do a marathon. Let's just go all in on this video. I'll give you some examples, but I give you this list over here. I said empty, point, line, plane, space. You might be saying, is everything covered here? Is this everything? Is everything covered? It seems like this is kind of pointless to have this fundamental theory if everything is going to be included. But really, like I said, right, if we suddenly put x squared on one of those values, you're going to see how it's not going to be included. Let's go ahead and do that. So let's say we have minus x squared plus y plus, let's go with minus, it doesn't really matter, but let's go with minus 1. Really doesn't make a difference. Is equal to 1. There we go. Just cover it to the other side. And then here we have x plus y is equal to 2. So this is still a system of equations. Still a system of equations. Because system of equations just means a bunch of equations that you're going to have together. But it's not a linear system of equation. It's not linear. Because to be linear, you can't have these exponents on your variables. This is going to disqualify you. Disqualified from the linear club. From linear. So if you automatically see, if you're asked, is this a linear system of equations, and you see an exponent on any of your variables, they're cheating, they're not allowed, and they're disqualified. And I'll show you an example, right? So we want to know if this is a linear system, and we're going to want to know by the answer, right? By the fundamental theorem of linear algebra. So we're going to go here, and we're going to try to graph this out, right? So we're graphing this first one over here. This one is a straight line. The second one over here, I should say. So the second one, I'll put it over here. It's going to look something, I don't know. I'm just going to freeway this. There we go. Freehand. It's not nice. It's all over the place. That's the first one. And then this one over here is going to look, it's going to look curvy, because that's what happens when you have exponents in it. So it's going to look something, I don't know, like this. And now we want to know, right? The answer is going to be the intersection points. So go ahead and highlight those intersection points. We have one over here and we have one over here. Well, you might say, yeah, that's got to be allowed. Those are 2 points. The 2 points are your answer. But if we go back over here, your answer is 1 point. Your possible solutions is 1 point, not 2 points, right? If you're going to have multiple points, it's got to be a line or a plane or something, right? And in this case, for this to have been a linear system, you'd have to have this whole line being included. But it's not. So this is not going to be a linear system. We can see right here that it's not, because of that to the power of 2 that we have. So this is an example of where it's not going to qualify. I'll give you one more example in 3D, right? This video has ran on for like an hour, so it's may as well just go ahead and stay here all night. So let's go ahead and get some 3D over here. Right, again, here we go. Freehand this ugly straight lines. Yeah, we go. At least I hit the center. I don't even have enough room to do what I want to do. So say we had 2 shapes, right? I'm not going to write the equations for these, but say we had a plane and we had, I don't know, some type of, not cone, but you'll see what I mean, like a cup shape here. So let's get that cup going. I don't know what you call this. Nice little cup. There we go. So say we had this guy over here and we had a plane. The plane will be over here. So is the intersection going to be a linear set? The intersection between this, and it's not going to, because let's go ahead and draw it out. It's going to be the circle where they meet up, right? So the circle where the plane cuts through this shape that we have here. This is going to be what's included, right? Included. Now that's a circle, right? So if we go back to that, list that we had over here, this little, shopping list, let's go ahead and check off where we see the circle. Well, that's not a circle. That's not a circle. Well, that's not a circle. There's no circle allowed here. So that should show you that this clearly here, this was obviously made using some exponent values. This was not made using just X, Y, and Z, right? To make this shape here, you had to have some 3's to the power of 3's, right? You couldn't have just made this just straight up like that. So anyways, that's to show you, what a linear system is in the fundamental theorem of linear algebra. It's like, I hate videos like this. They're abstract. They don't deal with actual numbers, but we need to do them to understand the concept. So if you were asked the question, like, is the orbit around the sun considered a linear set? Well, no, we don't have that included in that answer that we have over here, that shopping list that we had on top, where we had empty space, point, line, plane, space, and so on as it goes up the dimensions. So thanks for watching. If you have any questions, leave them below. This is one of the videos. Don't hesitate to ask questions, because it is a little bit abstract. And I hope it got through to you. If you enjoyed the video, if it taught you anything, please subscribe. It means a ton. And I'll see you guys in the next video.